The speaker has been Bakker, who will tell us, we wrote down his title.
Great, thank you. Thanks for the introduction and the opportunity to speak. And the opportunity to be here this semester. It's been a great semester. So yeah, I want to talk about some questions related to the topology of complex algebraic varieties. Okay, so let's X be a complex algebraic variety. Okay, and just to be super concrete, you can keep sort of as an example in your head if you like, just the zero set of some polynomial. 0 is equal to x to the mod to the d. This is the degree d from our hypersurface. Just inside of c to the equals 1, dimension n. But somehow I want to talk about any complex algebraic variety, so it might be, the zero set of many polynomials, or it might be zero sets of polynomials glued via sort of polynomial transition functions. Okay, so that's what the general object is. But in particular, sort of polynomials are holomorphic functions, and therefore we may consider X as a complex analytic variety, namely sort of locally the zero set of holomorphic functions glued via holomorphic transition functions. We may view it as a complex analytic variety. Or we might just view it as a topological space. Here I'm sort of taking the classical topology on C, inheriting the topology from there. And here's an extremely vague question that I might be interested in. Sort of generally speaking, sort of, how does the topology interact with the algebraic and analytic structures? More pointedly, I'm going to be interested in the fundamental group. So the sort of vague question I want to ask is, how does the fundamental group, which is of course just an invariant of the underlying topological space, interact with the sort of algebraic or the analytic structures? Namely, its structure is either an algebraic variety or a complex analytic variety. Okay, so this is an extremely vague question, and I'll write down some more still vague but more precise questions in a second. I do want to point out that it is sort of important for this to be interesting in some sense to take X to be normal, which, if you like, sort of complex analytically means that it satisfies a version of Riemann extension, sort of bounded holomorphic functions extend regularly. What is the reason for that? Well, if you allow for arbitrary singularities, you can do sort of arbitrary gluings. So the fundamental group will have sort of some combinatorial part that just comes from those gluings that you do. And you can basically get any fundamental group if you allow arbitrary singularities, and it doesn't interact with the sort of algebraic structure as strongly as it does if you don't allow those gluings. So for instance, as soon as you take X to be normal, it is not true that you can get any finally presented group as the fundamental group of a normal algebraic variety, even though you can get any fundamental group from not only a normal, but in fact, a smooth complex analytic variety. Okay, so this is sort of an important restriction to kind of remove the combinatorial part, which sort of isn't controlled by anything.
Wait, sorry, what did you say? There is or there is no difference between the class of fundamental groups you get as normal and smooth?
For algebraic varieties?
Yes.
There, I don't know if there's a concrete example written down, but you would expect there to be a difference between sort of normal and smooth algebraic varieties. Yeah, I don't see a reason why they would be exactly the same.
What does normal mean?
So as a complex analytically, it satisfies Riemann extension. So as a complex analytic space, locally, if you have a bounded holomorphic function, then it extends regularly. That's the simplest way to think about it. If you want to think about it algebraically, it means that the local rings are integrally closed. Questions? Okay, cool. Okay, so as I promised, let me give two more precise but still vague questions. So X is a complex algebraic variety, and therefore a complex analytic variety. The universal cover of a complex analytic variety is naturally a complex analytic variety, but not necessarily algebraic. Okay, so question one is sort of, if I take the universal cover, sort of how many global holomorphic functions does it have? Put many in quotes. Does the universal cover? Still the half. Okay, so this is purely a question about X tilde as a complex analytic variety, sort of how many global holomorphic functions does it have? But I'm only looking at these complex analytic varieties that arise from universal covers of algebraic varieties. And here's another question, which is again sort of related to this theme I mentioned over here. How many simply connected algebraic subvarieties does X have? Subvarieties does X have? Okay, so again, this is sort of related to the algebraic structure and the fundamental group. It's not clear that these questions have anything to do with each other. But the sort of story I want to tell will tell you that in fact these questions are related. And by telling the story, we'll sort of understand what I mean by many in both contexts. Okay, so let's start off with some examples where we can actually maybe say something. Let me slide one thing. Let's talk about the dimension one case. Okay, so in dimension one, we know that X is a possibly punctured Riemann surface. It's a Riemann surface that has a genus, say genus G. Maybe it has some punctures. Say it has n punctures. And there's the usual trichotomy related to the sign of the Euler characteristic. So the Euler characteristic is 2 minus 2g minus n. And let's see. So this can be positive, can be 0, or it can be negative. Okay, and at least if there are no punctures, this is sort of related to, whether it's positive curvature flat or negative curvature. So what are the possibilities for X? Well, in this case, I can have the Riemann sphere. Or I can puncture the Riemann sphere once and get just the complex plane. If I puncture another time, though, the Euler characteristic becomes 0, so that's over here. So that's C star, punctured complex plane. Or I could take a genus 1 Riemann surface, no punctures. And sort of the biggest category is over here, where I'm allowed to take the complex plane minus at least 2 points. Or a genus 1 surface minus at least 1 point. Or a higher genus curve minus any number of points, including 0. Okay, so those are sort of the possibilities. we can sort of understand very concretely what the fundamental group is in all these cases. In this case, they're simply connected. This is 1. Here, it's abelian. In fact, here it's z, and here it's z squared. And here it's not abelian. It's either a free group on sort of more than one generator, or it's a surface group if there are no punctures of a genus 2 or higher curve. And then we can also kind of explicitly understand what the universal covers look like. Well, in this case, it's the same thing. You either get P1 or the complex plane. Here we get the complex plane, and here we always get the disk. Okay, so sort of as if we sort of want to understand these two questions on the dimension 1 case, well, first of all, question 2 is a little silly because there are no sort of strict algebraic subvarieties of X, except points, which are simply connected. So it's whatever. It's just any point. For question 1, we can just read off sort of what the global holomorphic functions on the universal cover are. On P1, it's compact, so any global holomorphic function is constant. And if you're either the complex plane or the disk, seems like there's more holomorphic functions. There's many holomorphic functions, and in a way I'll make precise in a second. So, you know, based on this, but some higher dimensional examples that I'll get to in a second, sort of Shafarevich, around 72, made the following conjecture. It's a far-reaching conjecture, but it's well, I don't know what the right adjective is, but it's regarding question 1. Maybe it's an optimistic conjecture. Maybe that's the right word. Which suggests that, well, in general, we just kind of have a combination of the two phenomena we see here. So for X, a smooth, compact algebraic variety, the conjecture says that the universal cover should be what's called holomorphically convex. Okay, so what does that mean? I.e., there exists a proper, we may as well take it to be surjective holomorphic map. You say F tilde, let me say this, F tilde from X tilde to Y tilde, where this Y tilde is Stein. Okay? So in this one-dimensional example, both the disk and the complex plane are Stein. And so is a point. So I mean, in the one-dimensional case for P1, this map would just be trivial and would be the identity for the other two cases. I won't tell you the usual definition of Stein, but I will tell you that it's a non-trivial theorem that Stein implies that you're a closed sub of some affine space. Okay, so in particular, that means you have lots of global holomorphic functions. In particular, there's enough global holomorphic functions to separate any number of points. Lots of global. Okay, so this is the precise sense in which I mean there are many holomorphic functions, global holomorphic functions. There are on Y tilde, there's enough global holomorphic functions to separate any number of points. Of course, this map is proper, so the fibers are compact, so I'm never going to be able to separate points in the fibers. But being holomorphically convex at least tells you that you have enough global holomorphic functions to separate points up to compact ambiguity. Sort of set of points that have the same value for all global holomorphic functions forms a compact set. Okay. So I said this is not the definition because already for the disk, it's non-trivial to see that the disk can be realized as a closed sub of C to the A. So that's really a theorem, but sort of if you want to think about what it means, it's as good sort of a definition as any.
The characterization of Stein or
There's many. So if
is this like being the closed subset of?
yes, yeah, it's if and only if, yeah. Like I said, it's usually a theorem. It's not usually taken as the definition, but that is an equivalent with a small nuance related to the embedding dimension. Another way to think, the Stein is kind of an analytic analog of affine in algebraic geometry. Another characterization is the higher cohomology of any coherent sheet is zero.
Is analytics submanifold or algebraic?
Sorry?
It's analytics.
No, an analytic, yeah, closed analytic subvariety of CP. That's right. For the questions. Okay, so this is an answer in some sense to question one. What I want to point out, this is an observation that at least goes back to Kovar, which says that there's a relationship between this conjecture and sort of question two, which is the following. Well, there's sort of a reason I called this F tilde from X tilde to Y tilde, and that is I can take the quotient by pi 1, that gets me down to X. But because this is proper surjective, in fact, pi 1 acts discretely on Y tilde, so I get a reasonable space downstairs. I take the quotient. Okay, and since everything's compact by Gaga, this is in fact an algebraic variety. So this is an algebraic map. Okay, so we get this algebraic map just by taking quotients. And this algebraic map satisfies an interesting property. Namely, if Z inside of X is closed with finite image on pi 1, so the image of the map on pi 1 to pi 1x is finite, then it's in a fiber of F. An exclamation point. Maybe that's surprising. So why is that? Well, if we have this closed algebraic subvariety of X, if it has finite image on pi 1, well, it may as well have trivial image on pi 1, in which case Z lifts all the way up to X tilde, right? So now we have a compact subvariety of X tilde, and yet any 2 points of Y tilde can be separated by a global holomorphic function, and any global holomorphic function is constant on that compact subvariety. So Z must be contained in a fiber. I guess I should say it's closed and connected. Okay? So we get this map, and it has this strong property that any subvariety with finite image on pi 1 must be in a fiber. And in fact, every fiber has this property. So in other words, this map is giving us the algebraic family of all maximal subvarieties with finite pi 1 image. So i.e., there exists an algebraic family of I don't know if I have enough space to say a maximal sub with finite pi 1 image. So it's a little, I won't do this on the board, so I crammed it a little bit, but hopefully you can read that. This is a non-trivial statement that if you take that there's an algebraic family of maximal subvarieties with finite pi 1 image. It's some important boundedness result. I mean, already for surfaces, let me say, you can kind of spell out what it's saying for surfaces. So for example, if X is a surface, let's say a smooth projective surface, then we might be interested in genus 0 curves inside of X. And what this is saying is that if pi 1 of X is infinite, well, it means that if this is true, then this Y tilde must be either 2 or 1 dimensional, in which case we conclude that the only 2 possibilities in terms of the behavior of genus zero curves is that either it's fibered by genus zero curves or it has finitely many. Okay, so they're fibered in P1s or there's finitely many, which this is still not, I mean, there's many special cases in this known, but it's still not known in this generality. And moreover, it's not, this dichotomy is not always the case. For instance, for K3 surfaces, you have countably many rational curves, but no family that contains them all. Okay, so already we're seeing this sort of fundamental group here is implying some boundedness statement about families of algebraic subvarieties with that are either simply connected or more generally with finite image on Python. Okay, so that's kind of interesting. Let me leave these questions on. Erase this. Okay, so that's all great. So what can we say in higher dimensions? Well, it's kind of hard to say anything about pi1. So as usual, maybe we want to study pi1 through its representations. Pi1 of x is hard. So maybe we want to study representations. I'll call them rho x, meaning from pi as let's say a complex representation of the fundamental group. And how do we, okay, well, that begs the question, sort of, how do we make representations of the fundamental group? Well, one way to make representations of the fundamental group is with families of algebraic varieties, okay? Algebraic families over X give representations of the fundamental group. Okay, so let me give you an example of this. I think, let me put it over here. I just erased what I want to talk about, but I want to prove for you that C minus 2 points is uniformized by the disk as an algebraic geometer would. Okay, so let's consider, let me put this over here. Let's consider C minus 2 points. Let's call that X. C minus, may as well take them to be 0 and 1. Here's 0, here's 1. Let's say our parameter downstairs is lambda. Okay, let me cook up an algebraic family over this base. And that family is the family of these cubic equations. So y squared is equal to x times x minus 1 times x minus lambda. Okay, so this sits inside of c squared with coordinates x, y, sort of with parameter lambda. X. Okay, and for all lambda that aren't 0, 1, or infinity, this topologically looks the same. It looks like a genus 1 surface with 1 puncture. Okay. So now if I consider the universal cover of X, I should draw this little down. Consider the universal cover of X. I can pull this family back, and now over a simply connected base, I can topologically trivialize it. So I can, it's homeomorphic to just the trivial family of this one punctured genus 1 Riemann surface cross X tilde. And in particular, I can choose some basis for the first homology. That would be alpha. This one would be beta. Okay. And also, I can write down an algebraic one form in this family, dx over y, which for any value of lambda is sort of a regular one form. In fact, it completes regularly over this puncture. And so now I can write down a holomorphic function. Namely, I'm going to take the integral of this form along beta, right? So I've trivialized the family upstairs, so it makes sense to talk about this loop beta in every fiber of the family. And I take the ratio with the integral over alpha. This gives me a holomorphic function because this is an oriented basis. I mean, this always has to have non-zero imaginary part, but because it's oriented, this in fact lands inside of the upper half plane, which is just the same as the disk. And you can show that this is an isomorphism. Okay. And we get a little bit more. So where does this representation come from? Well, the sort of fundamental group acts by deck transformations here, then will act on this sort of trivialization of the family upstairs. In particular, it'll act on this basis. So I'll get a representation from pi1 of x into SL2Z. Okay, and this will act on this upper half plane because it acts on the ratios by Mobius transformations. And this quotient, by the image of this representation, is just isomorphic to the x we started with. So that's how this picture plays out in the particular case of C minus 0, 1. And the point I want to make is that sort of for an arbitrary x, given an algebraic family, which is also sort of topologically locally trivial, there's a very similar story, which goes back to work of Deline and Griffiths, and it falls in sort of the world of variations of Hodge structures and period maps. Let me just basically just going to draw that same diagram, but over here, so we can record it for later. So in general, if I have some family W over X, a topologically locally trivial family, topologically trivial family, space, say locally trivial, say topologically locally trivial. And I can choose some base point and some reference fiber over that base point. Okay. And just as over there, upstairs on the universal cover, I can topologically trivialize this family, in which case I can take a trivialization of the homology, and given any algebraic form on the fibers, I can take integrals. Okay, so by taking ratios of integrals, I will get a map to a holomorphic space called the period domain, which essentially parameterizes very vaguely sort of ratios of integrals. I need to be more precise than that at the moment. This is what's called a period map. And just as over there, it's sort of equivariant with respect to a natural representation by looking at how deck transformations change the framing of the first homology that you took. So this sort of lands in GL of the, let's say, the kth homology of X. Sorry. Like that. And just as over there, I can look at what happens downstairs. So I get a period map from X to the corresponding quotient of this holomorphic, this complex analytic manifold by the image of this representation, which it turns out acts discretely. Okay, so this is sort of a reasonable complex manifold. And so far, everything looks pretty.
Example for projective base.
Sorry, say again?
Develop singularity, how this example on base compact.
Sorry. So,
His example was base compact projective. Because he is not projective, yeah.
yeah, well, here I'm not assuming X is projective.
But how you give the example?
Oh, but you want an example of a period map where you were
Base projective. Then it's hard to get, huh?
you can make such examples. So, for instance, if you can find compact subvarieties of AG for which you would get such a map.
If you have moduli space where infinity can be of smaller, not of codimension than one dimension.
Because exactly have a singularity when you remove it, I understand, but how you make it everywhere. This family.
You take a moduli space of a billion variety, principally polar. You have a compactification where infinity is of codimension van bigger than one.
Yeah.
Then you can find
Okay.
some curve.
Okay, yeah, that's right. Yeah, so AG admits a compactification with high codimension boundaries that you can find curves. Great, okay, so this picture looks a lot like this picture, except I don't have isomorphisms in the horizontal arrows, which there's in some sense a reason for that. There's an unfortunate fact in this general situation is that this is no longer in general an algebraic variety. It's not algebraic. Okay? It's not so bad though, because in fact, you can take the image of this map and take just its closure. And Griffiths showed that this is in fact a reasonable complex analytic submanifold of this quotient. So you have a map X to Y, what we call it F. And it is true, so this is the theorem with Johann Brunebarbe and Jacob Tsimerman from a while ago, that this Y is algebraic. So X, Y, F is algebraic.
I'm assuming that you start with a family of projective or at least compact varieties.
So for this result,
Yes.
this is in fact true for any admissible mixed variation of Hodge, the period map of any mixed variation of Hodge. Yes, so you can take basically any kind of family you want. Other questions? Okay, cool. So why is this relevant to the story I'm telling? Well, first of all, this period map phi, or rather this map F, this algebraic map F, has the following property. Sort of F is trivial on a subvariety of X, if and only if the image of this representation is finite on Z. If and only if pi 1 of Z, once again, I'm going to run out of space. Okay, so let me just say the composition pi 1 Z goes to pi 1 X goes to GL is finite.
And what exactly does it mean that Fx to Y is algebraic?
Meaning Y has an algebraic structure. In fact, I mean, this is a complex analytic variety. So it admits an algebraic structure. In fact, it admits a unique algebraic structure. And with respect to that algebraic structure, this analytic map is algebraic.
Oh, okay.
Yep. Okay. So this map has the property that for any subvariety, this subvariety is in a fiber of this map if and only if the representation when restricted to that subvariety has finite image, okay, which is very similar to this behavior we saw over here, okay? And the reason for that, so this is sort of a theorem about, I mean, ultimately due to Deline, that for a period map or for a variation of Hodge structures, the period map is trivial, namely the variation is isotrivial, if and only if the monodromy is finite on and 3, so now we have this Y, which sits inside of here. We can look at the pre-image in D. So that's a certain cover of Y. What cover is that? Well, that's the cover sort of coming from this representation factors through a representation of the fundamental group of Y. So let me just call this rho Y. And that representation then gives me a cover, which I'll call Y tilde rho Y. And this is in fact Stein. So I won't get into why that's true, but essentially the reason for that is this is a sub of here. And this period domain has the property that it has sort of negative curvature in the directions that Y moves in. And therefore you can find sort of a compact, strictly pluriself-harmonic exhaustion function. And that is one way to show that you have lots of holomorphic functions on this thing, okay? So we found that this map F is the family of maximal subvarieties on which this representation is finite image, just like over there. And we also found that the base of this family has lots of holomorphic functions, just like over there. Okay, so this picture for period maps sort of very much kind of jives with this conjectural picture for when you sort of assume the Shafarevich conjecture, what you would then get downstairs. Okay. So in fact, there's an implication too. If X is proper, then this map is actually proper. And if the representation is faithful, then it will follow that the universal cover is holomorphically convex. So in fact, if your X is compact and admits a period map for which the monodromy representation is faithful, you can actually conclude the statement of the Shafarevich. Okay, so that's all great. But, you know, I mean, representations that come from geometry are somehow very special. Sort of, or, you know, aren't they? Aren't representations, aren't rho X coming from geometry very special? The answer is, well, of course, but the answer that non-abelian Hodge theory might give you is that they're not as special as you might think. So I want to spend the remainder of the time talking about why that's true and why it's relevant. Not as special as you think. Okay, and so let me state some theorems that basically say that this picture that I have here essentially holds for any representation, not just a representation coming from a family of algebraic varieties. It's actually better. So here's the first theorem. This is again with Johann Brunebarbe. So this is last year. Okay, it says that take a normal algebraic variety, X, and take any representation of its fundamental group for any row X from pi 1 X into GLR, C, any complex representation. There exists a unique algebraic map, F, from X to Y. So this is an algebraic map. So I'll say algebraic. Such that the representation factors through a representation that lives on Y. So rho X factors through rho Y, and rho Y is large and non-extendable. Okay, so let me tell you what that means. So large, this is a notion that goes back to Collar. Large means that on any positive dimensional subvariety, the image of this representation is infinite. This means infinite image on any subvariety. What does non-extendable mean? Non-extendable means there is no partial convectification of Y to which this representation extends. Rho Y doesn't extend to any partial convectification. Sorry, I'm trying to cram it in. But
F with dense invariant.
Sorry, yeah, this is just a like a dominant map. Yes, yeah. This is dominant. Thank you. And it has connected general fibers of connected. Yeah, that's good. Otherwise, it wouldn't be necessarily unique. But these are so this large and non-extendability are sort of the two obvious things that might obstruct such a map from being unique, such a Y from being unique. If there were some sub on which, let's say, the representation is trivial, you could imagine contracting that subvariety to get a smaller Y. Or if there were some partial convectification to which you could extend the representation, then you could, extend this map by making Y bigger. And what this theorem is saying is that you can contract all subvarieties along which the representation is finite image, and you can add as much boundary along which the representation extends. And you should think of this as sort of producing, for any local system on an algebraic variety, or for any representation of the fundamental group of an algebraic variety, producing like a minimal model for that local system. Okay, so it's a unique algebraic variety which comes with the representation for which it's maximally non-trivial on all subvarieties and can't be extended. Okay, so this is essentially like saying any representation of the fundamental group has an associated period map in some sense, right? Because it's a map which is contracting everything along which it's trivial and which extends it as much as possible. Okay, so that's theorem 1. And theorem 2, so this is sort of an answer to question 2, right? Because it's telling you, once again, that you have an algebraic family of maximal subvarieties along which this representation has finite image. Theorem 2 is about holomorphic functions on the universal cover. This theorem says that any local system comes from one on which it's large and non-extendable. So let me state theorem 2 in this way. This is also with the same authors in the same paper. If some normal algebraic variety Y admits a large and non-extendable representation, rho Y, then its universal cover is Stein. Then rho tilde, so actually slightly better, the minimal cover on which this representation is trivialized is Stein, but any covering space of a Stein space is Stein. So this implies that the universal covers. Okay, so this sort of addresses question 1. Because it tells you, well, once you contract all the subvarieties on which this representation is finite image, then you have lots of holomorphic functions. Okay, so for instance, as a very simple corollary of these two theorems, this is kind of a simple statement that you can sort of take away. Whenever you have an algebraic variety which has a representation of its fundamental group with infinite image, then the universal cover has a non-constant global holomorphic function. Because if it has an infinite image representation, by this theorem, this Y is not zero-dimensional, and then by this theorem, it has non-constant homomorphic functions, which you can then pull back to X. Okay, but you might say, what is the, if you're ultimately interested in the Shafarevich conjecture, sort of what is the statement that you can extract in that direction? Here's a corollary. The statement is that if X is a normal algebraic variety which admits a faithful representation of its fundamental group, then the universal cover is what you might call quasi-holomorphically convex. Quasi-holomorphically convex, by which I just mean it's a Zariski open inside of a holomorphically convex thing. Okay, so in particular, this Shafarevich, this version of the Shafarevich conjecture assumes X is compact, so that phenomenon does not arise. If X is compact, or more generally, if this map is proper, then X tilde will actually be will be holomorphically convex. But in general, the most you can expect is that it's
It's open universal counting, not algebraic.
yeah. So like analytically, Zariski open. So the complement of a closed analytic subvariety. Yeah, that's right. Okay. And somehow, if you want to think about this Shafarevich conjecture in the non-compact case, they're sort of forced. I mean, the reasonable conclusion or the reasonable statement of the conjecture would be that the universal cover is quasi-holomorphically convex. Because, for instance, if you look at something like c squared minus 0, right, it's simply connected, but it's not holomorphically convex, and but it is quasi-holomorphically convex. That's the kind of thing that connects. Okay, so let me remark that the sort of this idea of kind of using non-abelian Hodge theory to address this question in the compact case goes back to earlier work of so for X compact. This is the sort of the end product of a long series of sort of a lot of work on non-abelian Hodge theory, starting with Simpson and various other peoples, and sort of ending with the work of Isidiu, Tsarkov, Pantev, and Ramachandran. This is from around 07, I think, but it published later. Which does theorem 1 and 2 for either a semi-simple representation or a faithful one. Theorem 1 plus theorem 2 for rho X semi-simple or faithful. Actually, that's kind of a cool thing that I meant to mention. In this theorem, if you assume rho is semi-simple, then in fact this Y is quasi-projective. So somehow all semi-simple representations of algebraic varieties, of fundamental groups of algebraic varieties, come from representations of fundamental groups on quasi-projective varieties, and that's related over here in this variation of Hodge structure setting to the fact that here, if you're dealing with a pure variation of Hodge structure, you can prove that Y is quasi-projective. Okay, so those are sort of the main two theorems that I'm. So anyway, yeah. So large cases of this were proven. I mean, for rho semi-simple, the whole thing, and then in the non-semi-simple case, they have to assume it's faithful. But this was done sort of in the compact case. So the main point here is upgrading this to the non-compact case, which sort of takes advantage of a lot of advances in the past 10 or 15 years on sort of non-abelian Hodge theory in the non-compact case. So I want to give you an idea of why those techniques are relevant. Sort of the key. So the key point is to understand the sort of harmonic theory of representations of the fundamental. Okay. Why, I mean, vaguely speaking, why is that coming up? Well, that kind of goes back to this point 2 over here, which is somehow the fact that you have this relationship between the map being constant and the monodrome being finite is ultimately an expression of a maximum principle. Sort of produce some harmonic, some bounded harmonic functions on an algebraic variety, which are then forced to be constant. And that's kind of built into what's going on here. And it's going to be a similar phenomenon that's important when dealing with an arbitrary representation. Of course, if I just have a random representation of the fundamental group, there's sort of two pieces of this story that are kind of independently missing. So first of all, the fact that it underlies a variation of Hodge structure, so comes from a period map, is one thing that's missing. But also the fact that it has sort of integral monodrome is another piece that's missing. So when we do the harmonic theory of a general representation, we're going to have to do it at both the Archimedean and the non-Archimedean places to sort of recapture both sides of that story. Okay. Let me start. I don't know, maybe I'll erase this. Okay, so let's first talk about the Archimedean place. I'll be pretty abbreviated in this because there's not so much time left. But what is the setup? I want to take a complex vector space, let's say. I mean, technically real or complex, but let's take a complex vector space. And I want to take a representation on V. So a representation into GL of V. Okay. And what additional structure can I equip this representation, or equivalently this local system with? Well, I can give it a harmonic metric. Okay, so there is a space. The way I want to think about this is there is a space, I'll call it delta infinity, infinity for Archimedean of V, which is the space of sort of unitary metrics on V. Okay, and if I have a map from the universal cover, or whatever, the cover on which this representation is trivialized, to if I give myself an equivariant map from there to there, that's the same as in equipping the corresponding local system with a metric on every fiber. And I can ask for this map to be harmonic. Okay, so I can ask that, and in fact, it is a theorem that there exists a harmonic map, equivariant map, I'll call it psi rho x, for any semi-simple representation. And this is due to the work of many people, right? Sort of Corlett and Donaldson in the compact case, and Simpson in the non-compact case for curves.
Do you reduce to x being non-singular?
Yeah, you basically immediately reduce to by taking a resolution. That's right. And in the higher dimensional case, in the non-compact case by Machizuki more recently. I'm sure there's many other names to put, but let me at least put that. So that's great. Except, this is like a symmetric space, right? This is like GL mod the unitary group. Okay, so in particular, not holomorphic. And it would be nice to have some holomorphic maps. Luckily, these period domains that I wrote down before, that are luckily still on the board, live over these symmetric spaces. So a Hodge structure in particular gives you a certain metric on your underlying vector space. And we can ask for which harmonic maps lift to period maps. The answer is, of course, not all of them. But any representation can be deformed to one that lifts to a period map. So again, running out of space. We'll use this whole board. So this goes back to Hitchin and Simpson in the compact case, and then Machizuki. And then also our paper in the non-compact case. So rho x can be deformed to one that lifts to a period map. And that's good news, because again, now it's harmonic, and we're mapping to, and we have a holomorphic map which is related to sort of this harmonic map in a certain way. So it obeys a sort of maximum principle. So we have a phenomenon very much like this, except there's no integral structure on the representation. So the conclusion here, when you have a period map for a variation of Hodge structure that doesn't have an integral structure, the correct statement is that this map V will contract the subvarieties along which the representation has compact image. So contracts V inside of X on which rho X has compact image.
To speak of harmonic, you have to put in a Kähler metric.
Yes, I mean, so in fact, there exists a pluriharmonic map, which will now only depend on the holomorphic structure. But yes, to talk about the harmonic one, you need to equip this with a Kähler metric. Has compact image, and then so in this Archimedean case, compact means unitary. So the way you should think about these period maps is they contract subvarieties along which the representation becomes unitary. Okay, great. So maybe I'll erase maybe theorem 2 because I want to sort of maintain the parallelism here. So now what is the non-Archimedean story? Well, sort of what is, well, now I'm going to have V, well, let's say a QP vector space, but more generally sort of any discretely valued complete field and a representation. Okay, and what should I put here? So delta, I'll call it delta sub P of V. And this should be the sort of non-Archimedean version of a metric. So an ultrametric norm. This is sort of an ultrametric norm. Okay. And what does this space look like? Well, let me concretely tell you what it is for the rank of V equal to 2. So usually I draw the picture for P equals 2. But given the recent weather, I'm going to draw it for P equals 5. And it looks sort of like this. Okay. So it's a Bruhat-Titz building, so it has this sort of local Euclidean structure, except there are some singularities where sort of different Euclidean pieces come together. And what is the statement here? Well, once again, for any semi-simple representation, if I go up to the sort of trivializing cover, there exists a harmonic map here. Psi rho X. And this goes back to work of Gromov and Schoen. Many names to put here. Gromov and Schoen, maybe also worth putting Korovar Schoen. And then also, sorry. Jost Zuo, so this is mostly in the compact case, and then more recently in the non-compact case, this has been worked out by Diskalopoulos and Messe. Also Brockback. Also Diskalopoulos. Dang. Okay. And then also we have to add some stuff too. So let me say plus epsilon times. And strictly speaking, so in general, in the compact case, it's for semi-simple. In the non-compact case, you need a condition at infinity, namely quasi-unipotent monodromy. Maybe I'll sweep under the rug. Okay, so that is a picture that's kind of analogous to what was happening over here. Once again, this is sort of not a holomorphic object. So I would like to get a holomorphic map. The story is a bit different in this situation. What one shows, basically because of the locally Euclidean structure, that there is an algebraic map from X to, I'll just call it A. This is called the Katsarkut-Zuo reduction. This. So this is an algebraic map now. So over here, so this is kind of playing the role of this map. It's not an algebraic map, doesn't even live on an algebraic variety. So this is a complex analytic map. And I had to deform the representation to get it. Here, this just exists. And this is an algebraic map with the property that an algebraic subvariety is contracted if and only if the representation is compact image, now with respect to the non-Archimedean topology.
So this A again, this A.
So this A will be a quotient of the sort of, you take the minimal quotient of the Albanese from which the one forms that you get from here are pulled back, up to the finite monodromy of the things, and then take the quotient. So it makes sense downstairs. This is a quotient. This is like an abelian variety mod, a finite quotient. Z contracted if and only if rho x is compact image on Z, which in this case means it has an integral structure, i.e. has an integral structure. In other words, this is EP lattice. Okay, so over here, we're producing some maps that sort of contract things such that the representation is unitary. Over here, we're contracting things along which the representation has an integral structure, and unitary plus integral is finite. Okay, so if I sort of naively, if I put these two things together, I should get something which contracts all the subvarieties along which the monodromy is finite. And that's indeed, so I won't say, let's take 2 more minutes to describe the sort of last leg. So putting these two together, I get some kind of map, by taking a bunch of representations underlying, that have associated period maps that underlie variations of Hodge structures. I get a bunch of these sort of holomorphic period maps. From any sort of QP local system, I can get this map, which sort of integrates out the things along which it's integral. So let me just put that here. So this is the sort of moral of the story. This is like a period map. Like a period map. In the sense that, so you can't literally take the quotient down here, but you can take a Stein factorization and this map will descend nicely to the map you're after. So let me just point out, I haven't mentioned O minimality in the story at all, but it's extremely important in this to just like here, sort of a big input here is the sort of definability of period maps. Similarly, in order to make this work, you need to use, in the non-proper case, sort of definability of these complex period maps that you get. And so then you do some work. So you use O minimality, various other things to produce this algebraic map. But one thing I want to end with, and sorry, I'm already a little bit over time, is that I kind of swept something under the rug. I said, like, starting with a representation, you can deform it to get this period map. So it's not the original representation. And here, I can't even necessarily start with the original representation because it needs to be a QP local system, a QP representation. So the kind of remaining thing to do is to show that both of those things, either the QP local systems or the ones underlying variations of Hodge structures, are somehow dense inside the moduli space of representations. Okay, so need such rho x dense in the space of representations, which is just some algebraic variety defined over Q, because it's just Homs from this finitely presented group into GLR. Okay, well, of course, this will have lots of Q bar points, and therefore it'll have, just by taking some finite place, it'll have, replacing QP with some finite extension, there will be lots of non-Archimedean local systems, so that's not the problem. The problem is that somehow, when I deform to get things that underlie period maps, I might have to go far away. So they might be pretty sparse. And so the fix there is to show, this is done by Isidiou and Simpson in the proper case, and then we do it in the non-proper case, that sure, these points that underlie period maps might be sparse, but actually the formal thickenings of those points still underlie variations. Of course, the full infinitesimal thickenings are dense in the modular space. Okay, sorry. Way over, I'll stop.
Any questions to Ben?
Yeah, which part of the Archimedean part applies to some infinite dimensional representation of particular kind. Yeah. You know, the Sioux theorem applies to infinite, and probably there is a parallel part for the non-Archimedean also, if we can extend it to some.
That's a good question. I don't know. I haven't looked into that. But I vaguely remember someone telling me that there is some version.
Because part of the harmonic theory applies when the target is infinite dimensional.
Yeah.
And there are infinite dimensional symmetric spaces. They're beautiful and they take the same kind of structure. But
Yeah.
they definitely not algebraic, but
Yeah, I think, is Bruno here? I think Bruno had a student who thought about this, but anyway, yeah. So I'm not sure. I've never thought about it myself, but I think there's something there, yeah.
I want to make sure I understand this. So you said that if X has a non-compact p-adic representation, then after a finite cover, it actually has an infinite cyclic extension.
Yes. Yes, I can tell you.
That's not obvious, right?
No, it's not obvious at all. And the fact that you can sort of algebraically integrate these two. I mean, let me just give you 30 seconds of where this comes from. So this has this local Euclidean structure. So you have these sort of one form, these natural flat one forms here. Okay. And if you pull flat one forms back under a pluriharmonic map, you get pluriharmonic one forms, which are the real parts of algebraic one forms. So now I'm in the world of algebraic one forms. And you know, those are always pulled back from the Albanese. There's some quotient thereof, and that's how you build this map.
you know, the K form for higher rank, they do the K forms, right?
Well, sorry, I should have put a crossbar here. Yeah. So it's true that in general you get a symmetric form,
Symmetric form.
but it always splits on some finite cover.
Ah,
And that's why this finite group comes in. So if you go up to a finite cover, you have an actual map to an abelian variety, and then you take the finite quotient and get a map.
No questions. Okay, thank you, Ben, again.